Welcome to the course Algorithmic Design. So we can try to do, I don't really have an exact example, but something like, yeah, it's basically this we'll try to do. Or so we'll try to do this kind of field averaging, which will give us this sort of flow lines. And yeah, maybe a result might look also a little bit something like this. And usually when you look sort of online for these examples, they would call them kind of attractors, but here I don't really like to use that term because they're not really attractors, but it's really has to do with sort of defining a field and having elements arrayed on that field, and then these elements are somehow responding to the field, and this produces these different sort of flow effects. Okay, so that's the goal. So we will start with this. We import again the RhinoScriptsyntax library, run geometry, and we do this enable redraw to false. So so in Rhino we can draw our kind of boundary. Or so let's draw some boundary. So I go here in the rectangle, origin 0, and then let's make it maybe 100 by 100. Okay. So this is our kind of boundary here. Actually, delete the grid here again. I sometimes don't really like this grid, so I'll just turn it off. Okay. Okay, so yeah, that's here. And this is our boundary. And we just have to make sure that we'll take this boundary and we'll actually call here in Rhino file, we'll just call it something like boundary. Okay, and we'll give it some nice color, something neutral, maybe white even. Okay, and we can select this rectangle and just say, you know, I can actually just go down here. It's covered. Okay, change layer in Rhino and switch to boundary. Okay, and then what we can do, we can actually lock this boundary. Okay, so now we cannot kind of select anything inside. That's basically our square where things will happen. And we know that it starts at the 0, 0 origin, and it goes like 100 by 100. Or so it's just that we are, that's a bit easier for us to see what's kind of happening. Okay, there's the default layer, and we will also have, we'll delete these layers here. We will have a layer called input. Okay. So those are going to be some input vectors, and we will change the color maybe to some magenta, something that's we can easily see. Okay, and we can now draw some lines here. Or so I can draw a line, maybe like this, maybe like this, maybe similar to what we had in the example, in the picture. Okay, so these are some lines, and if I select them and write dir, so that's the direction, it's also here in Rhino, somewhere here, I think, analyze direction, or so I can just write dir, shows me the direction of these lines. Also, in Rhino, as well as in all the kind of CAD software, their lines have, or geometry has a direction. So there's kind of start and there's the end. And this is true for surfaces, curves, lines, for like everything. Everything kind of has a direction. And we can use this as a convenient way for us to basically pretend like these are vectors. Or so you can pretend like these lines are sort of vectors for us, and their direction is basically the direction of the line. Or so these vectors now point like this, and that's going to be our input. But we will actually work in this default layer. Or so we have the input, we have the default layer where we will sort of draw everything, and we can, yeah, so we can kind of distinguish between what's created and what the sort of input for the script is. Okay, and okay, the first of all, let's create, let's input these. So these inputs, let's kind of get them in. Also, let's get them into Python. So we can call them, we can just say lines equals rs dot get objects. So there's a function called get objects, and this function will prompt us to select things in Rhino, and we can put a prompt message in, or please select input vectors. Okay. So, and if I can just say also print these lines. Also, this is going to be some. Be careful here to use get objects, so plural. So it'll prompt you to select kind of multiple objects. So when I run it, it says please select input vectors, and we just select all three of them. Aha. I just also realized that this enable redraw needs to be underneath this get objects. Okay. The reason is because this enable redraw, if you put it to false, we can't really see what we are selecting. So when we have a selection in the script, we need to sort of enable the preview, so or enable the redraw so we can select things. So it needs to be underneath. So if I run it again, I can select these three objects, press spacebar, and that's it. Here I'm just kind of printing them, or printing the GUIDs. So those are these kind of codes, and I kind of have now access to these three objects. Okay, and I can, for example, convert these three lines into vectors. Okay, so the way I can do this, I can build a small loop. I can say for line in lines. So what this does, it will iterate through the list of lines, and it will give me individual, kind of unpack individual lines inside individual objects, and it will I can then manipulate them inside this loop. And there's a function called rs create vector. So we have to be careful. There's like a create vector and there's vector create. These are two different things. Vector create. Okay, so we have to just be careful which one we use. Let's actually have a look in the cheat sheet here. Create vector. Let's see what this one does. It says converts vector into okay, no, we need vector create. Let's see. Okay, yeah, this is better. So vector create says creates a vector from two 3D points. That's it. So if I have 2 points, I can get a vector, and this should be a vector 3D then at the end. Okay, so vector create we use. We need to put 2 points. Also, there's kind of some kind of start point and end point. Okay, and this will be called vector. But the question is, what is my start point? What is the end point? Well, it is the start point of the line and the end point of the line. And for that, there's also a function. Start point is rs.curve start point. Okay, so there's also a function called curve start point, which returns the start point of the curve object. And here, when you say curve, it just means like lines are also curves. Lines are curves, they're just straight. Okay, there's a start point of the curve, and there's the end point of the curve. There's a similar function called rs.curve endpoint. Okay, gives me the endpoint of the line. I can also get the midpoint, and there are some other ways to also I can get kind of points in between as well by using evaluate curve and so on. So I can basically, if I have a line, I can get every coordinates of every point on that line. Okay, and again, there also might be a function that converts basically a line into a vector, but this is good enough for us. We see what's happening. Okay, so we get the vector, and now we will create an empty array. So there's going to be an array called vectors, which is going to be first defined as an empty array, and then we will say vectors.append. Vector goes in. Okay, so we will have a collection of vectors. So vectors is just a list which contains individual vectors inside. That's it. So again, I like to use plurals and singulars because then I know what's inside the lists. But these lists, you can call them however you want, or so it doesn't really matter. Okay, and the cool thing is that now I have a list of lines and I have a list of vectors. Or so if I run this code now and I print them out, basically now I have a list where I have a line, kind of a Rhino line, and then I have a corresponding vector. But actually also, unfortunately, I realized this vector create, out of some weird reason, it flips the vector. So now this, for example, the vector for this line points toward the negative quadrant. That's why these two coordinates are negative instead of toward the positive quadrant.
Yeah, I think it was different. It is 2 point from point.
2 point from point. Okay, let me see. Aha, great. Okay, thank you very much. So yes, I find this a bit counterintuitive. 2 point from point. Okay, so so basically we have to give first the endpoint and then the start point. I find this counterintuitive, but yeah. So it is. Okay, so if you flip these then in vector create, there's endpoint and there's start point. We will get now, if I run it again, they should all have positive components, which means that they point toward the positive quadrant. And again, actually go back to my amazing lecture. So I kind of gave you here some tips also in this slide here in the lecture. You know, upper left, these are the quadrants. So this is the positive quadrant here, 1, and then they're just labeled, but this is the negative quadrant. So you can kind of peer a little bit where the vector points by kind of knowing which quadrants are positive and so on. So, okay, so that's kind of a little bit here. Nothing hard, just some high school geometry, analytical geometry. Okay, let's go back. So now we have lines and we have vectors, and that's basically it for this first part. I can just put a small comment, create vectors corresponding to input lines. Okay, so we create vectors corresponding to input lines. Here I can just write get input lines from Rhino. Okay, perfect. And now, so this print is just to see what's happening. Okay, and now I want to somehow map an influence. So I want to map, I want to basically average this field. Or so now I can say, if I draw, so if I have a line here, I want this line to be somehow influenced by the vectors that are closer to it. And to do that, I will do something that is called field averaging. So I will kind of average the whole field. So every point will contain an average of like the weighted average of the field. So if I have a vector that is very far, it might not be influenced by any of these vectors here because it's very far. The closer I get, it will start to turn, and then maybe when I get very close to the vector here, it will start kind of turning in the direction of the vector that is closest to it. These ones here will be they'll be kind of turned in according to the vector that is closer to here, and these ones will be turned like this. And then I will get in between. I will get kind of all the states in between, something like that. So this one will be exactly in the middle, and so on. So this is what I call field averaging. It might be a bit better mathematical term for it, but it is, every vector is basically being influenced by all the other vectors, but in a graded, in a weighted way. Or that means I'm basically measuring. If I, for example, look at this vector here, I'm looking at the distance from all the vectors. So distance to here, and distance to this one here. And all of these, they influence this vector here. They're all, sorry, my Rhino just snagged. And I can just see what happens when I run this. Select input vectors, perfect, okay. So let's go on. So basically now what I want to do, I want to draw all of these vectors. So in order to see what's happening in the field, I have to draw these sampling vectors, and I want to draw them all over the field. And of course, I can draw them wherever I want because my field is continuous. But I cannot draw infinitely dense, or so I'll just choose a grid and I will just draw them according to some according to some kind of density that I choose. Okay, and for that I need to go into a next line. Also, this now works. The top part works. I am now creating create sampling vectors. Okay, so I'll create these sampling vectors, and for that I need some kind of grid extensor. So I need again this kind of a grid or sort of a cell size, or so it's going to be some size of the cell, maybe 1. There's a cell number. Okay, so that's going to give me somehow size of my grid. Cell number is maybe 100. Okay, so I can say for x in range, and that's going to be my cell number. And because it's a two-dimensional grid, I know that it needs to be a kind of nested loop, or so I go x and y direction, or for some cell number. But actually, because I also might want to skip some, I can write like this: 0 to cell number, and then there's some kind of a step, or there's a cell number, cell size, and some kind of a step. In this case, let's put it to, let's not do it too dense, so maybe we do it to 5. So it's going to be like 20 by 20. Okay, step. So there's going to be a step here as well. So again, in this range, I can choose the beginning, the number, total number, and then the step size for these numbers. Okay, step is 5. Okay, so first I can actually just draw points, or I can draw individual points. That's going to be easy. So there's going to be some kind of a, again, start point, rg dot point 3D. And the coordinates I kind of know. That's my x times my cell size. And for the y, it's going to be y times cell size. And then the z we don't worry about now. So we don't worry about the height. So I'm putting it to 0. Even though, again, this just the fact that we left the 0 here and we work with sort of three-dimensional vectors enables us to extend this into 3D, even though we can also work with a flat case if we want. Okay, so we go, so that's my start point. And now I can just say sort of, rs dot add point. So just to quickly sort of add it to the document to see how this grid looks like. And if I run it, select my vectors, up. Okay, this is how they look like, and there's a bit of the grid doesn't really go to the end because I start with sort of 0 and kind of end here, but I can actually change this. I can go all the way to the end by just adding here cell number +1, cell number +1. Okay, so if I do this, now if I undo and run it again, now I should go, now my kind of points go sort of to the end here. But now, of course, when I draw my vectors, these vectors will kind of come out, or so that's maybe, but it should be fine. So I can choose kind of how to create a boundary so that my vectors are kind of inside and not going over the line. Okay, but now basically each of these can get a vector attached to it. Okay, so how do we do that? Well, again, we can add a point, but these points are not really that important. So we'll just comment it out. So I want to create an average vector, or so. So what is an average vector? Average vector is basically adding all of these vectors. I want to kind of get a resultant of this vector here first. So you can imagine that if, again, these are vectors, or right here, dir, so they have this direction. The way I add them, I just kind of do this. So it's also, this is commutative, so it doesn't matter in which direction, in which order I do this. So dir, this is the resultant, or so I can just go line from here to here. This is the resultant. So when I add these three vectors together, this is the result. Okay. but this is only when I add them. So when I just add them, not depending on. So if I just add these three vectors, this is the result. But I already said that I want to do a weighted average, or so that means if I have a point here, then it's not only adding them together, it is basically measuring the distance to these vectors. Or so these vectors have a distance, and the question is, of course, now, well, how I measure? Do I measure distance to the beginning, or to the middle, or to the end? We will do it. I think it's best to do it to measure. We'll get the nicest results if we measure to the mid point of this line, or so. That's, I think, going to be, it's going to be nicer, just kind of graphically, it will look best. So I actually need these midpoints, or so these midpoints of the lines, I need them. And I will, because I always need to calculate them, it's maybe better if I calculate them once and then just use them over and over, because the midpoints of these input vectors, they will never change. Or so the same as I have here, in this first loop, I have start point, end point. I also want to actually have a midpoint, or because I already see that I will need it. So I can just say midpoint. And again, there is a function called rs.curve. Curve midpoint, okay? So, and start and end point here, I don't need to save, because I just got my vectors, that's what I need. But I actually need to save midpoints because I will need them later. So I can just create another array called midpoints. Okay, so I do it before, midpoints is here. And the same as I'm kind of adding these vectors here, I can have midpoints dot append. So basically anything in the code that I need to save, I can create an empty list before, and I can just use append to add them all in. Of course, here there are 3 lines of only 3 points, so it's not really that impressive. But the good thing here is that this vector and these vectors and these midpoints are now matched. Or so if I these are 2 lists that are matched, meaning that the first vector in the vector list has the kind of midpoint in this list is also the first point in that list, or so. So they are kind of matched. So if I know the index of the vector, I can already get the midpoint of the line. Okay, so now we're going to create this weighted average. So I'll have like another small for loop where I will actually iterate through the vectors. Or so I can say for maybe vec in vectors, or actually let's do it differently. Let's do it something like for I in range length. So length of this vectors list, or maybe the lines list, whatever. So if I have 3 lines, this number will be 3. Or so, and this is now going to be my index I, and this index I can use to iterate through line number 1, line number 2, line number 3. Okay, so that's kind of the trick. So if I say now vectors I, this is now my 1 vector. Or so the first vector, if I say midpoints I, this is now the midpoint corresponding to that vector. Or so I'm not really interested in lines anymore, but only into vectors and their midpoints. That's the trick. And yeah, I need to just add them all. I need to add them all together. So maybe before, so I need to create this again in the here. It's a bit hard to see, but basically I have a point here, and I'm adding these vectors together, and I'm kind of dividing them with these with the distance. Also, I basically need a vector sum, so I can just create something like vec sum, or it's called vec sum, and vector sum is basically first we will start with vector 3D, and it's going to be a 0 vector. Okay, so if I write it like this, I now have a 0 vector, or so it's basically like a 0. Yeah, I have the kind of 0, my 0 vector, and I can just now add other vectors to this, and it's basically like calculating the sum. Okay, so I can do something like, you know, vec sum equals whatever this first vector is. So I just add it there, but I want to divide it with the distance, or so maybe before I can calculate the distance. Distance is rs dot just a minute. Yeah, there's a function called distance, which measures the distance between two 3D points. Okay, the first point is my start point. That's kind of this point here, or that's my start point. And the other point is it's the midpoint, or it's the midpoint of this line. So I'll just copy paste it here. Okay, and that's my distance. And then I have vec sum is basically my vector divided through distance. But I might want to raise this to the power of 2, we'll see. But for now, maybe you can just keep it as it is. So now this is a scaled vector, and I add it, of course, this is not correct. I can add it to my vector sum in Python doing this. So I can say vector sum plus equals this, which means that I'm adding this thing to this kind of scale vector to the vector sum. Okay, and I'll do this 3 times because this number is 3. This vec sum will then go from 0 to be some. It'll become some value. Okay, and that's basically my test value. Will be this kind of weighted sum, or so it'll probably go in some direction like this. And then I just have to draw it, or I have to draw it like a line. I cannot really draw a vector, but I can draw a line, and I can draw a line by just saying, well, end point of this line is basically start point plus vector sum. Okay, so if I have point and the vector, if I add a point to the vector, I'm getting a translated point. So it's almost as if I move that point. So, you know, I move this point here from here to the end of the vector, which is here. That's it. And then I will get like a small line, and then I can draw that line. I can say just rs dot add line, and that's my, again, start point, end point. Now don't be confused that I'm using the same names. So there's the start point, end point here, and there's a start point, end point here. These are separate things. Okay, I'm just kind of rewriting them. I'm just reusing the names. I can do this because I don't really need the start points here and end points here. I don't really need them. That's why I didn't save them here. I just saved, you know, vectors and midpoints. So I can just continue. In this way, I'm kind of reusing the names. They're just overwritten, or so I don't have to worry that they are the same names. Okay, and that's basically it. So that's kind of this should already work, and I'll just try it quickly. And then if that works, then I can maybe elaborate a bit further. Okay, I'll just save this. We have to make sure that we are in the default layer. And if I run this, I will probably get very large lines or very long lines. Oh, okay, they're not that long. Okay, so you can see a little bit what's kind of happening. I can actually make it a bit denser even. So here we have step 5, maybe do step 2. There are not so many points. Okay, so if I go closer, you can now see that I kind of seeded. I seeded these sort of vectors, and when they're closer to the input vector, they kind of take over the direction. So they start going in the same direction, and then they're just basically going in the direction of the vector that is kind of closest. And some of them are a little bit. These are this is a problem with these singularities, or some of these vectors will become very, very large. The closer they are to the midpoint, they'll become very, very large. And in theory, if there's a vector that hits exactly the midpoint of this input vector, we will get an error, or so the length of the vector will become infinite, or because this distance, if the distance to the mid vector here is 0, then this becomes 0. So it means I'm dividing something with 0. And as you know, in mathematics, you're not allowed to divide with 0. Basically, you get a very, very large number, or in a way, infinite number. It's not really defined what you get, but you will for sure get an error. But basically, the closer these lines get to the midpoint of the input vector, they'll become longer and longer. And these are basically these kind of these are these singularities that I was talking about before. Basically, if I have again electric charge, the charge is not really defined well in the exactly at the point where the charge happens, because the distance to that charge is 0, and then in a way the force is infinite. And that's why kind of in physics you do this renormalization. And of course, quantum mechanics postulates this sort of granular nature of space. So somehow the things can be resolved. But basically, if you could hit the point charge exactly at the exact coordinate, which we cannot, but if you could, then the force would go infinite. And that's, of course, we don't observe this in nature, so we know that it doesn't really happen. Okay, let me just increase a bit step size more. So if I just run this again, you can see a little bit what I'm talking about. Now some of these lines will become very long. Yeah, okay, so these are these singularities. They're kind of they basically, you can think of them as sort of points where the vectors become infinitely long or very, very long. And they're not exactly what we want, or so we want to, we might want to filter them out, or so, but we can do that maybe in the next step. So this is the first kind of a very, very rough step. Just step 2 like this. Okay, so that's for sure the first one. Okay, let's clean this up a little bit. So I'll actually save this as a kind of version number 2. We'll try to clean up a bit. So for example, we can try to filter out these singularities by basically, let's see what happens actually when we flip this guy. So now this guy points in the opposite direction. If I run it, you'll get a different result. So now I have these lines go here. These lines, they kind of sort of turn, or there's a certain curl happening here. It's maybe a bit more interesting. Let's kind of renormalize this. So we can say something like, there's something like maximum length, or so here something like, or now let's call it a minimum distance, or so there's something like min distance. There's some minimum distance, and we will minimum distance equals just run this. So we can define a minimum distance. So maybe something like, yeah, maybe like 1 would be enough. So we can say minimum distance is 1, maybe 1.0. What does that mean? That means that if this distance here that we calculate, if it becomes smaller than the minimum distance, so we can say if dist smaller than min dist, that we just defined up, which is 1, then dist equals min dist. Okay, so I wrote it now in here in 1 line. So in Python, this is allowed. If you have a conditional with only 1 line, you can write it like this, but you can also write it like this. It's a bit kind of more compact. This just means that if this distance that we measure from this vector point to the midpoint of the line, if this is smaller than whatever the minimum distance we define here, then we'll basically define it as being this minimum distance, or so we sort of have a cutoff. When you go below this number, the numbers will be fixed. So we cannot go, 0.5 will not be allowed. 0.5 will snap to 1. And in that way, we basically fix the minimum distance, which should prevent our vectors from becoming too big. Yeah, so if I run it again, now we should not get, let's actually see here, if I go step 1, maybe I can increase the minimum distance a bit. Yeah, so you can see the longest ones don't exist anymore, but I can maybe also say minimum distance is maybe 5. So now there's going to be like a, yeah, okay. So I kind of, basically there's now a circle, like a radius, like influence around the center point, which is somewhere here, I guess, here. The circle that basically prevents these vectors from getting too large. Maybe 5 is too big. Maybe we can leave it to 2. So this is some form of renormalization, or so we kind of avoid singularity, but basically saying if the distance is too small, then cut it off and make it then just be this minimum distance. So it's a bit kind of a discrete cutoff, but we just use it to sort of avoid weird things happening here in the centers. Okay, and so that's how we kind of sort of renormalize. And actually, okay, and that's maybe the last addition. Actually, I will save this. I'll save this as number 1 because maybe this is a good addition to it. And number 2, I'll just delete now. Okay, and so those are now these sort of small vectors, but this is not really what we wanted. So this is just now defining the field. Also, the field is now defined. In every point, there is a value. There's in a way a vector for every point. But what we want to do, we want to create trajectories. Or so we actually, what we want in the end, we want to have like some kind of a curve or like a point that sort of starts object snap. Okay, we want a point that kind of travels, or so we want to start with 1 point, and we want to sort of see how this point would, in a way, move through this vector field if we would sort of follow these vectors. Or so we're already going to, yeah, we're basically going to use these as sort of like force lines, and our points would be sort of charged particles which are kind of moving through this field. Okay, something like this. Maybe if you start here, a point would kind of follow these vectors, and then somewhere here it will start to slowly curve, maybe like this. Okay, yeah, this is not actually that bad. Okay, it's a bit hard to see actually the direction here, but depending on the direction, okay, the particles will sort of go and curve around. Okay, so that's actually what we want to do, because these vector fields that you see here, that's basically what's happening here. There are kind of these sort of particle lines, and also here, and there was another example, I think here, yes. So these are basically sort of these force lines, sort of like particles that are kind of traveling along the field. So that's what we want to do. And for that, we need to kind of create now this simulation, or so we kind of have to create a traveling particle. Okay, and that's the last thing that we'll do today. And so this is field averaging 1, and I will save it as field averaging trajectory. Okay, story. Okay, field averaging trajectory. Okay, so with trajectories. Okay. Okay, so that's the next step. Let's remove these. Okay. Here, very quiet today. If you have questions, you can also, of course, ask. And yeah, I mean, I imagine that you might have already got lost a little bit, but hopefully I'm trying to keep this code as neat as possible so that you can go through it a little bit on your own later. Okay, so create sampling vectors. Great. So let me see. Okay, so so to create these trajectories, here, instead of creating sampling vectors, we have to do something else. We have to basically say create trajectories following following sampling vectors. Okay, so we are not really creating these small vectors anymore, but we are somehow we are, let me just see. Yeah, we will use this formula to basically we'll use this formula, but basically we're not anymore kind of creating a grid, but we will, well, actually, no, we can actually create a grid, yeah. So we can say our starting points are the same as sort of before, but we need to sort of now also move, or we need to kind of move along this field. Okay, for that, we need to rewrite this a little bit. So maybe this is the start point, okay? And this is the end point. And we need to actually create a small loop again within the loop, or so there's some kind of for, and maybe we call it n in range. And here we have already step. Maybe we call it something like step, something like trajectory steps. Okay, so there is going to be a variable called trajectory steps. And that's basically how many steps we will use. So how many times will we move? So when I say a trajectory, I mean this, or it's going to be a line, and then there are going to be steps in between. And then we can just decide how many steps we want to have. We need to fix it because we cannot go, otherwise we can just go infinitely. We can just kind of go on and on and on. Or so we need to fix the length of these steps. Trajectory steps, maybe we put it to 10. That's a kind of a nice number. It's not going to blow up. Step 1, maybe here, step 2. Okay, trajectory steps 10. Okay, so whatever is happening here needs to now happen. So we calculated sort of step by step by step, but this we need to know now. We need to do this 10 times. Okay, so actually we can define maybe a start point outside. Okay, there's some start point, it's here. Then we again create this vector sum, la la la. There's a start point, and then there's the end point, and we are adding a line. But actually, this add and line we are not adding here because we're not interested in these lines. We're interested in kind of a polyline, or so maybe there is a start point, and there's some kind of polyline points, or polyline points is an empty vector. So we will just add polyline points dot append. We will just add this start point into it first. That's the first thing I'll do. Okay. And at the end of these loops, we are going to have some kind of, we can just say, you know, polyline equals rs dot add polyline, same as yesterday or last week. We also use this add polyline. We need to give it points, or so these are going to be my polyline points. So that's what happens at the end. But we need to create all the points first. Okay, so there's a start point added, then we go on and we calculate sort of the end point, which is start point plus vector sum. Great, but we need to now add this endpoint as well inside, or so polyline points dot append endpoint. And now the trick is, well, we are not over, or we just did one step. So we need to do, you know, here we will do over and over multiple steps. So basically, we need to do this small trick, which is basically start point equals endpoint. Okay, and now when we go back into the loop, now basically our start point changed. Our start point is not anymore the same. Here, I'll say here, create trajectories following sampling vectors. Yeah. Okay, so these trajectories are actually created inside here. Here, the trajectory points are created. Okay, start point equals endpoint. So we are using the endpoint as a kind of a new start point, and then this will happen now 10 times, and then we should get a polyline, like a polyline line, which we can then use to draw, to draw the whole trajectory, and maybe later we can try to make it a bit curved. So we can change the degree of it to turn it into like not make it kinky. Okay, let's actually try to see if this works. So you see, we didn't really add a lot. We just changed very, very few things to create these trajectories. Let's see how this happens. Okay, yeah, it works already. Okay, yeah. Okay, I will just do it now a little bit differently. So let's say we have steps of maybe 5, and trajectory length is, trajectory step is maybe 50. So we can change a little bit how this looks like. Okay, yeah, this works for sure. Trajectory steps 50, step maybe, yeah. So now the question is only, yeah, so, okay. Again, it is a little bit hard to see. I'll actually try to make it bigger. Okay, so now these individual lines are actually polylines, and they're actually kinky. It's a bit hard to see, but there's kind of a kink here. Maybe we can also turn them down kind of to make them smooth. And according to also diagram that I showed you before, so they don't really look like this, because here we have sort of a sources and sinks. So our example does not contain that, but we are more working in this kind of paradigm here, where sort of the lines will never intersect, or so we have this situation here. And again, if you go a little bit closer in, these lines, they don't intersect, or so, I mean, they could maybe intersect only due to imprecision of kind of drawing in Rhino, and but if you would kind of have an infinite precision, none of these lines should intersect actually. So you will never see them cross. They're just kind of yeah, well, as I said, some are crossing, but this is only because the way the steps are calculated. You can see here the step is, between this point and this point here, so it's quite a long step. So they could cross only due to that, but otherwise, if you would have again infinite precision, these lines will sort of, they are kind of coming close to each other, but they don't really intersect. They're kind of defined. So every point in this field has only one vector, one vector associated with it, one direction. If you would have lines that cross, this would mean that for a single point, there are somehow two vectors that are defined for it, which is not true. There's only one vector defined for every point here. And that's why we get this kind of a sort of a smooth, it's basically just kind of increasing the density. Okay, and of course here we get this weird result because this input vector points toward up, this one points toward down. So if you remember, I'll just actually go undo. If you remember, for direction, these one on the top points up, and one on the bottom points up, and this one points kind of the opposite direction. And that's why when you run this, you get this kind of a, okay, I'll go back here. That's why when you run this code, you get this kind of a curling effect, or because the field is sort of shifting. The field is shifting direction, or so from here going up and then going down, and then yeah. And you can now play a little bit with this code. So I'll upload it again on my courses, and you can change the directions of these lines. So I can maybe just do it here, change the direction of this line. Again, this is not very. If I change the directions of the line a little bit, I will get a different result. You can see this curling is again happening, but a little bit differently now. And just. Okay, and one more. If I kind of now turn it to go more or less in the same direction, and if I run the whole code again, you will see that they will start to align. Yeah, so now they're kind of going all in the same direction. And yeah, that's it. I can, of course, just copy paste these and just kind of rotate them a little bit. Okay, so now I have a lot more of these vectors. And I will get a bit funnier situation probably. Let's see. So I select and say direction. Now they go kind of down, up, down, up, down, up. Or so they're going to create quite some shear action. If I run it, maybe it takes a bit longer to calculate if you have more input vectors, but okay. So you get kind of a really funky situation. Or so down, up, then back down, back up, and so on. And here I maybe want to just quickly show you how to smooth out these lines. Also, these are now kinky lines because our polyline here, if I go here under cheat sheet, polylines are by default kind of kinky, or so. Let me just see add curve. Let's see what that does. Okay. So I can actually, instead of using add polyline, I can say add curve, adds a control points curve to the object. Let's see, degree free. So maybe instead of add polyline, I can just say add curve. And this should maybe create a bit smoother result. Let's see. Okay, let's see. Yeah. These are kind of smooth, but again, there's intersection. There are intersections, but again, this is only because my steps are quite large, or so. Yeah, my steps are large, so I get intersections. But otherwise, if I could work with infinite precision, have very small steps, and then scale everything down, these lines would never really intersect. It's just that here I'm kind of at the boundary of what's possible. Okay, and that's actually it.